Quick comment on the common formula you're going to see in your text for conservation momentum in a two-object system. That equation is m1v1 plus m2v2 equals m1u1 plus m2u2. I'm not sure your book uses u1 and u2. It might use v1 prime and v2 prime. But whatever it uses, that's what the equation looks like. And that's the equation people generally memorize and try to apply. And there's actually nothing wrong with that, but it's really, I kind of advocate, and I'm not going to count it wrong if you use that equation, but I'm going to advocate that you go to the, excuse me, most basic principle that your impulse momentum theorem, F delta T equals delta P. Since these objects exert equal and opposite forces on one another, that means that delta P1 equals negative delta P2. The changes in momentum of the two objects are equal and opposite. It's a system, an isolated system with just two objects, so that this all follows from that isolated system. Okay, and this only applies to an isolated system with two objects. The consequence of equal and opposite changes in momentum, of course, is that the total momentum before equals the total momentum after. Any change in one object is balanced by the change in the other object, so that the momentum remains constant. And then here, this is just a simple statement of the fact that the momentum before equals the momentum after. Okay, m1v1 is the momentum of the first, m1v2 the momentum of the second, both before collision, and m1u1 plus m2u2, that's the momentum of the first object after collision plus the momentum of the second object after collision. So there's a little ambiguity in that statement. I still think you're best off starting your thinking with the impulse momentum theorem. It'll get you used to a more sophisticated approach that's going to be more generally applicable to the problems you're going to encounter in the situations you're going to engineer eventually.